Hello and welcome to the course. My name is Samuel from the Department of Mechatronics and Systems Engineering, ATBU, and I deem it fit. It will be really necessary for us to talk about some of the courses we are going to offer next semester. It will be very important for us to brush through some of these courses, especially those that involves calculation like maths, some engineering, mechanical courses, and some EE courses before we resume. So, particularly this tutorial, we are going to be talking about mathematics, the one we are going to be taking next semester. So before I continue, let me give out some of the details about our next semester's mathematics. We are going to be taking only one math, 212, and the math is being divided into 3 sections, which is the first one, differential equations, the second one is like vector, and the third one like that. So majorly, the scope of this course is going to be what we are supposed to take next semester. The exercises are strictly from the handout. The definitions, no external things being introduced, so we have to be relaxed. Everything is circled around our next semester's course. So what we are going to be taking, we just have to prepare ahead. We don't know when the school is coming back, so I will advise us that as this course progresses, we should try as much as possible to follow each of the courses. If there's anything we have to do, if there's any exercises, we should attempt it as the course progresses. We are going to be talking about a lot of stuffs. If time permits us, we move to the second part and go to some other courses that are very important for us to touch before the semester resume. So, I said we are going to be considering differential equations, and majorly we are going to be considering ordinary differential equations. But these are being divided into some subsections, which is going to be the scope of this lecture. The first one is the first and second order differential equations. We are going to look at the definitions and some working examples under this letter. Number 2, we talk about the existence and uniqueness of solutions. We are going to see some definitions and examples under this also as the course proceeds. We have the method of undetermined coefficients. We have the method of variations of parameters. We have the series of solutions of second order equations. We have the general theory of nth order linear equations, and lastly we have applications of ordinary differential equations to physical life and social science. We are going to see this majorly towards the end of the course. We're going to go into our introduction. There are some definitions, there are some things we have to sort out here. First, we talk about the type of differential equation, which is, as I said here, we're going to be talking about differential equation majorly in this course. So there's a need for us to know the types, and we have the ordinary differential equation and the partial differential equation. They refers to ordinary differential equation as ODE and partial differential equation as PDE. So this is very important for us to note that there's a great distinction between ODE and PDE. Anyway, we are going to see much of this in later courses towards the end of the course. We are going to see the differences, how complex they are, how the questions are being structured, how the equation looks like. If it's PDE and it's ODE, how do you recognize them? They are quite simple, and we are going to look at it later in the course. Okay, as the usual tradition is, as we all know that we used to talk about some definitions before we start the course, the examples officially. We're going to look at some building blocks for this course. We take a look at some definitions, how some things are being related together, and the first thing we're going to talk about is the definition of what do we call a differential equation. They said an equation which involves differential coefficient is called a differential equation. That means any equation that involves a function of, let's say, the over dx in the first derivation, the second derivation, or third derivation, or fourth, or anywhere. So generally, any equation that involves the over dx is being regarded as what? A differential equation. Let's take a look at the first example, which says the over dx equal to 1 plus x squared over 1 minus y squared. You can see here that this equation has the over dx, which makes it a differential equation with the function of x and y. We also have x equal to d over dx, x square equal to x square d over dx equal to y sin x. This one is being expressed in the function of sin x, but once it have d over dx, we still regard this equation as what? As a differential equation. Now let's look at the third example, which this one is being expressed in the as the second derivation. You have d square y over dx square minus x square y equal to 0. This is what? A differential equation, whether it's in the first order derivative or the second order or the third order, is still differential equation. So we are going to look at how we are going to be analyzing these courses, some examples under them. Moving straight to definition 2, here they define what they call ODE for us, which is ordinary differential equation. They said an ordinary differential equation is an equation that contains one or several derivatives of an unknown function, which we usually call y of x or sometimes y of t if the independent variable is time. So whenever we have time variables, we refer to those equations as they actually express in the function of t. You might have seen something like this maybe in physics or courses like that. The equation may also contain y itself, which is a very unique property of ODE. It may contain a function of y itself known as x or t and constant. So we better understand it by looking at some examples. The first one is the y over dx equal to cos s. One thing you notice is that there's not actually much difference between this and what we look at in the first definition. So what we can draw from here is that what we look at in the first definition is the general definition of differential equations, but definition 2 is talking majorly about what? Ordinary differential equation. So all ODE, which is ordinary differential equation, falls under differential equations, whether they are ODE or they are PDE. So this one actually falls under ODE, which is what? Ordinary. There's no any external function. We have x divided over dx equal to cos s. We don't have any u or anything like that. So let's look at the second example, which this one is a little bit unique from what we saw in first definition. We have the square y over the x square plus 9y equal to 0. This one is in the second derivative, and look here, we have the function of y. As the definition said, they said the equation may also contain y itself. So here we have the function of y, which is equal to 0. Now let's go to example 3, where we have a little bit complex equation. Here we have x squared and stuff like that. So we see that this one contains the function of x, the function of y itself, which we do not see in equation or definition 1. Definition 3 for us to draw some things. They said partial differential equation is an equation involving one or more partial variables of an unknown function, say u, that depends on two or more variables, often time t, and one or several variables in space. They say that's what definition 3 under our definitions. So the first example we're going to look at here is this. Now we see that for the last example we talk about only x and y, but here another variable is being introduced, what? U. Partial differential equation, they are a little bit complex to analyze than ordinary differential equation. So here this one has external function, which is what? A function of u, which we did not see in the former examples. We also have another one which has a function of t. We can see that here, often time t and one or several variables in space. And the last one we look at is this example, which has a, t, u, and x. So these ones are partial differential equations. They're a little bit complex to analyze. As time permits us, we might talk about some of them as the course progresses. From what we have seen in those three definitions, there are some things we can quite draw out as summary, or let's say we should just take note of it generally, that ordinary differential equations may be divided into two classes. We have the linear and the non-linear. When we are talking about the ordinary differential equation, those examples we wrote the other time, we can say the first one is linear, the second one is linear, and the third one is non-linear. And the difference between this one is that linear differential equation, the ordinary one, they are quite simple to solve. We see that during the examples. And the non-linear ODE, they are somehow complex to solve, but everything is still simple if we put our minds to it. We're going to analyze some of the examples. Linear ODE and non-linear, we see how they differs when compared to PDE2. Formation of differential equation. I can say this is what we're going to be doing majorly in this section, as in they will give us an ordinary equation and we'll be asked to form the differential equation. The now say differential equations can be formed by differentiating the ordinary algebraic equation and eliminating the arbitrary constants, or can be obtained from physical phenomena. We are going to see this majorly when we start talking about the practice problems. They said differential equation can be formed by differentiating the ordinary algebraic equation. They are going to give us some set of equations that are linear without any function of the welfare dx or something like that. Then we are going to differentiate it and use it to form a differential equation. Now let's proceed. It's now high time for us to dive straight into some practice problem. We are going to look at some problems and we are going to analyze the problems together. Okay, now let's dive straight into the course as a whole. Let's dive straight into the examples by firstly looking at the first example, example 1. The question goes that form a differential equations by eliminating the arbitrary constants in the equation y equal to ax plus x squared. Now don't forget what we talk about when we already talk about how they form differential equation, which means we try to differentiate the constants. We differentiate the equation and we eliminate some constants, which will then leave us with what? The welfare dx, which you can say is a differential equation. So the first thing we are going to do here is to differentiate the equation y equal to ax plus a squared, as we have seen, as the definition said that the first thing to do is to differentiate the equation. Now if you differentiate y equal to ax plus x squared, we are going to get what? A. You all agree with me here that differentiating ax gives us what? A. And differentiating what? A squared gives us what? 0. Which is, and on this one is a squared is what? A constant. And if you differentiate the welfare dx y, we get what? The welfare dx. So we know that these are what? Equation 2, right? Now we have a here, we have ax plus a squared here. Now we can substitute equation 2 into equation 1. Now this is the first example, so let me, it's better for me to say some things. This is what we are going to be doing majorly in this course. After we have differentiated our main equation, we are going to continue differentiating until we reach a point whereby there's agreement or some kind of relationship between the equation we derived at and the one they gave us originally in the question. So here we consider that the one we get from differentiating this as a, which is what the welfare dx equal to a, and this was y equal to ax plus a squared. So there are some kind of relationship between this equation 2 and equation 1. We can substitute equation 2 into equation y, which is what we are just about to do. In other examples, we are going to see that after we differentiate for the first time, the thing will not work. We still have to differentiate again. But this one, it worked by differentiating the first time. So if you put 2 into 1, we are going to get y equal to the welfare dx squared plus the y welfare dx if this power of square. The difference is quite simple. This is y, this is a is what? The welfare dx, and this what? X plus a squared. This a and everything square. So we get that from substituting equation 2 into equation 1. Now we have to some kind of collect length times, make our work more organized. Let's choose to pack all the welfare dx to the left hand side and bring the y to the right hand side. So doing some collecting like times, we are going to have welfare dx square plus x divided over dx minus y, which is equal to what? 0. And this is going to be our final answer. This here is this. If you bring y here, y is going to change to minus, which is then equal to 0. Now example 2. I said form a differential equation by eliminating the arbitrary constant in the equation y equal to c e x. Now there are some technical issues we have to look at here. We have y equal to c e x. Don't forget, when we are differentiating ex, e raised to the power of x, we also have to, the answer is usually what? E raised to the power of x. And c here is a constant. So let's dive into the solution. We have differentiating the equation y equal to c e raised to the power of x as our equation 1. So as I mentioned, the definition of ex equals to what? Ax. So if we differentiate y equal to c e raised to the power of x, we are going to get what? d over dx equal to c e raised to the power of x. If there's any question or any issue here, you should send the question or any problem to the groups or to the forums. So as we did in the former example, we are going to substitute 2 in 1. So this is our y, which equal to what? Cx. Now here we have d over dx equal to what? C e raised to the power of x. If you put the value of x, c e raised to the power of x, as what? d over dx here, we are going to have what? d over dx equal to what? Y. Don't forget, y equal to what? C e raised to the power of x. So d over dx equal to what? Y from here. So as we did the other time, we bring y to the left hand side and we have d over dx minus y equals 0. So I hope this is very clear. If there's any question or any issue before we proceed, after this course, please you drop the question and we are going to look at it together. Now we are going to example 3. We have a little bit complex example here. This is example 3. Let's say form a differential equation by eliminating the arbitrary constant in the equation y equal to x plus a over x. What we're going to do here is just what I've been doing all this while. We differentiate what? Y, which is d over dx, differentiate x, and differentiate a over x. I hope you can still remember how we do all these stuffs. Now, as our first step, we differentiate the equation y equal to x plus a all over x, and we got d over dx equal to 1 minus a over x squared. Now, if something is very unclear, let me just take my time and explain it. We all know that differentiating y gives us what? d over dx equal to, if we differentiate x, that's going to be 1. Hope there's no problem. Okay, now if you differentiate a over x, you can just take up this and try to solve it on your own. If you differentiate this using quotient rule, we take this one as u, take this one as v, we are going to get our d over dx to be minus a over x squared. I did that here already. We take our a as u, take x as v. Now d over d x is equal to 0 because what? A is a constant. So differentiating a constant gives us what? 0. And if you are differentiating x here, we are going to have what? 1. Now using quotient rule, we have d over dx equal to v d u over dx minus u d v over dx all over v squared. Now our u is what? Our v is what? X d over dx equal to what? 0 times x here, not supposed to be minus, this is supposed to be x. Now minus u. What's our u? Our u is a. bracket dv over dx, which is what? 1 all over v square, and v square is what? X square. Now every of this is going to give us 0. So from here we have what? We have minus a over x square, and which is how we derive what we got here. So this is our differentiation of dy over dx. So now from equation 1 you can also draw out that a equal to x bracket y minus x. Now there's no any new thing here, there's no any formula. I just try to expand this. If I try to make this more linear, it's going to give us this. Just try to attend to that yourself. If we expand this, collecting the like times and doing the stuff, we are going to arrive at a equal to x into bracket y minus x. Now we have to substitute the value of a in equation 2. This is our equation 2, and we have already gotten a to be what? X into bracket y minus x from equation 1. Let's say this is our equation 3, right? If we say this is equation 3, now this equation 3, we got equation 3 from equation 1 by what? Making this equation linear, collecting the like times and bringing a to the left hand side. Now we now have equation 2. After differentiating equation 1, we have equation 2, which is dy over dx equal to 1 minus a over x square, which you have already seen I come about that here. Now if you now substitute wherever we see a in equation 2, we put this value, which is the value of a. So that is what I actually did here. So dy over dx equal to 1 minus x, which is this a. I put what? X into bracket y minus x, x into bracket y minus x over this x square, this is x square. So cutting, we have dy over dx equal to 2 x minus y over x, and that's going to be our answer majorly. Now as we are moving towards the end, let's go to another example which is quite serious. Let me say like that. Now, it said form a differential equation by eliminating the arbitrary constant in the equation y equal to a cos x plus b sin x. Now we see that here we have the function of some tricks, sine and what? Cos. It's very easy. Let me say like that. We just have to do what we have been doing all this while. Differentiate y, differentiate a cos s, differentiate b sin x. I'm very sure we still know how we go about all that. Now if you differentiate a cos s, you're going to get what? Minus a sin x. If there's any, as I'm always saying, there's anything that is not that clear, you can always drop a message. We are going to meet for us to discuss this later. And if we are differentiating b sin x, you are going to get what? Plus b cos x. So now we have not reached where we are going. There's no difference between equation 1 and 2 now. Equation 1 said a cos x plus b sin x, and equation 2 says minus a sin x plus b cos s. Actually there's no relationship between them. We have b here for cos, b here for sin, so we can't bring anything inside each other. So it will be necessary for us to differentiate again. So on differentiating again, you have this square y over dx square equal to minus a cos s minus b sin x. So if you differentiate this, we get this. Differentiating this, we get this. We hope everything is clear. Now we can try to bring out the minus, and this one is going to change to plus. So a cos s plus b sin s. So we can now see that this and this they now have some kind of correlation, they have some kind of agreement between them, only that this one has minus and this one has no minus. So now we can draw a relation between equation 1 and equation 3. So we now bring equation 1 into equation 3. This is our y, which is equal to this. And don't forget, this is equal to what? This. So we can easily remove this and put y. So writing that, we have the square y over the square equal to minus y. These are minus, which is a, and this is y from a. So if you bring y to the left hand side, we are going to have plus y equal to 0. I hope all these things is clear, right? So if you bring minus y to the left hand side, we are going to have this, which is the main differential equation we are asked to find. So this is how all this progresses. Now this is not the differential equation. We derive that from what? From this. This is just an ordinary equation with some constants, and we draw out our differential equation from it. So it's possible we change this back to this, which we talk about that majorly last session. So let's go to the last example, and this example I deliberately stop here because there are some exercises I want us to address together, and I would like us to come back to this example. Yes, because it's really, I deliberately do some things here. I want us to work out some of the stuffs ourselves. So if there's any question, we're going to raise it and we're going to address it together. I think it will be more clearer by that. So here we are to form a differential equation by eliminating the arbitrary constants in the equation y squared equal to ax squared plus bx plus c. The first step, as always, is to differentiate the equation, right? Now, if you differentiate the equation, we are going to get 2y divided by this equal to 2x plus b. We all know how this one comes about. That's our equation 2, right? We know how this one comes about. Now, there are different ways we can actually tackle this problem. It might look very linear, but there are some techniques inside the question that you have to draw out something. You might choose to square both sides before you differentiate. Do you get that? So you might choose to square both this to go with this, and you're going to differentiate this. And you might choose to go another way. That's why I say I'm going to leave this question for sometimes. If you tried the two ways, if you are not getting the answer we are drafting here, you can always say the question. People we are going to attend to it, friends and everybody that has a little idea about it. So if you differentiate this for the first time, you are going to have what? 2y over dx equal to 2ax plus b. As we will see in the last example, that right now we are unable to establish any relationship between this equation and this equation. There's no relationship. You have 2ax plus b here, you have ax squared plus bx plus c here. So there's no relationship between these two equations. That means we have to what? We have to differentiate again. So on differentiating again, we have 2 divided over dx squared plus y d squared y over dx squared is equal to 2a. This question is a little bit technical, so I want us to at least let's try our best and try to analyze all these steps. Don't just say you don't understand. First, analyze the step, try to solve it out yourself. If you get it, that's fine. If you didn't get it, you can always raise the question. And we have this, as I said earlier, by differentiating second time. Now again, we have 3 equations. This, let's say this is our equation 3. This is our equation 3. So we can't actually establish a relationship between this and this. they are all standing alone. We have 2ax plus b here. We have 2a here. We have another thing entirely here. So we still have to go again by differentiating again for the third time. So differentiating again for the third time, everything changes. It becomes a little bit more complex, a little bit more. We have some kind of relationship between those equations. And what after differentiating this, what we derive is that this as I'm saying, you have to solve out this thing yourself. If it's not clear, if you didn't get it, you can always address these issues together. So if you differentiate to a here, don't forget that's going to be 0. You know this is a constant, right? So everything here gives us what? This after some series of steps, some kind of arithmetic and the likes. So this by differentiation, as in differentiating the third time, so we are going to get the answer, which is this. Now here we collected like terms, or let me just say we performed some simple additions by adding this and this, since they both have the same coefficient. So we are going to add them. 2 plus 1, that's 3, to get the final answer. So if, as I'm saying, like, you have to try to address this question, especially this number 3 and number 5 yourself. If there's anything unclear, you can always reach out, and we're going to talk about the question together. So as I'm rounding off this class, these are the exercises. As you can see, it's still from the scope of the class. The handout will say the pattern, everything is there. It's a form a differential equation by eliminating arbitrary constants in the following: the first, second, and third. It's not a must you do everything, and it's a must you do everything. Let me just say that. And just try and attempt the question. If there's anyone that is not clear, the question will be addressed. That's how we are meeting, for us to share knowledge and gain some understandings. If you attempted anyone and it's not giving you the required result, or what you are looking at, if maybe you are not right or you are doubting, you can always ask the question, and we're going to solve the problem together. So as I leave here, I say prepare very well, stay safe, prepare for next semester, read your book, and may God protect us all. Thank you. Bye.